A very good morning to one and all present here. Honorable Vice Chancellor, Sir, Professor Prateek Sharma, our esteemed guest, Dr. Sucheendra Kumar, Vice President of Data Science and Engineering, Chief Technology Officer, SBX Technologies, Adjunct Senior Research Scientist, the Systems Biology Institute, Tokyo, Japan, Head of Department, Biotechnology, Professor Yasha Hasija, convener of the event, Dr. Navneeta Bharadwaj, all faculty members, staff, and students. We welcome you to the lecture series in biotechnology organized by the Department of Biotechnology, Delhi Technological University. Now I request all the dignitaries on the dais to please proceed for the lamp lighting. Now I request the Honorable Vice Chancellor, Sir, to please welcome our esteemed guest, Dr. Sucheendra Kumar, with a sapling. I request the Honorable Vice Chancellor, Sir, to please come and say a few words.
Good morning, all of you. And on behalf of the entire Department of Biotechnology and DTU, I welcome Dr. Sucheendra and thank him very profusely on behalf of all my colleagues and students for very kindly agreeing to be part of this distinguished lecture series. And in fact, I would also like to compliment Professor Yasha and her team, Dr. Navneeta, and all colleagues in Department of Biotechnology who have taken an exceptional initiative, I would say exceptional initiative in organizing, in basically translating a thought which we had uh, very informally discussed with Professor Isha to do something, especially where we can actually invite practitioners who are working in the area of biotechnology and share their experiences with the students, the undergraduate, postgraduate, and doctoral students, so that they actually get to know beyond the boundaries of the textbooks and the research papers that they read, the scope of the huge potential and scope of this particular discipline that it has, and expose them to the various opportunities that exist. That was the idea, and in fact, I'm very happy and very satisfied that all the speakers who have been part of this series are actually distinguished speakers, and I'm quite sure, given I consider one of the important indicators of that these have been well received by the number of students that one sees and the participants that one sees, and the eagerness that one sees on the faces of the participants. So, which I consider to be is an indicator that how well these lectures have been, and I'm quite sure that all these lectures have added some delta value to your existing knowledge. Uh, uh, and at times, what happens that the amount of information that comes through these lectures is huge, and at times it is not so huge. But even if you are able to take small takeaway from any of the talks, uh, one doesn't know where in your journey, professional journey, where it helps in terms of adding value, or even providing opportunities which through the talk or networking with various scientists and researchers who work in this particular field. So in the same series we have today Dr. Sucheendra from SBX Technologies, Japan, which I'm sure that through his talk there'll be again it is in continuation of what all the previous speakers have contributed and added to your knowledge base, which I'm quite sure the enthusiasm that I see with which he's eager to share his experience indicates that something really special is going to come your way. And personally, I would like to sit through all these lecture series because that is the best way to learn. Because obviously, in these days and times, it is very difficult to visit the library at times. Obviously, people like for teachers and otherwise, the best place for visiting library and referring to the research papers are the students, because that is the luxury that they enjoy. For teachers and who are occupied with administrative work, I mean, at times the time becomes something very premium and becomes very, despite of wanting to visit the library or even looking at the mobile, it becomes very difficult. The best way is to listen to people who are basically distinguishing themselves through their accomplishments and the contribution to the field, because in that 35-40 minutes, the density of information that you get is much more and larger than you otherwise get by referring to, because first of all, while reading, you have to understand each and every line and struggle at times to make a sense of what there is in the paper or whatever you are reading. But here you have the advantage of listening to somebody who is giving a talk on a particular topic, and obviously if you have any doubts, so directly through Q&A you can address those. So this is the best way of knowledge acquisition, and I'll go slightly philosophical in this. The best way in good old times when there was no printing was through this only, through discourse, and Upanishads are about this only, to speak and to listen and to discuss and debate. Thank you so very much, and I welcome on behalf of the entire team, Dr. Saab, and I do hope that the students get benefited from your talk. Thank you so very much.
I request the Honorable Vice Chancellor, sir, to please felicitate Dr. Sucheendra Kumar. Let's have a huge round of applause. Now I request the Head of Department, Professor Yasha Hasija, to deliver the welcome address.
A very good morning, everyone present here. Honorable Vice Chancellor, sir, who just left. Dr. Sucheendra, our honorable speaker for the day. Dr. Navneeta, the convener of the symposium. Professor Praveer Kumar, all the faculty members, and my dear students. It is always said that the strength of a university lies not only in its buildings or numbers, but in the conversations it creates. Today, as we gather for the 5th and the 6th lecture series in biotechnology, I feel a sense of pride seeing this hall filled with such energy, curiosity, and commitment to learning. The lecture series has now become more than just an academic event. It has evolved into a platform where ideas are exchanged, collaborations are seeded, and young minds are inspired to dream bigger. Our lecture for today will be delivered by Dr. Sucheendra, the Vice President of Data Science and Engineering and Chief Technology Officer at SBS Technologies, Tokyo, Japan. He is also an adjunct senior research scientist at the Systems Biology Institute. His talk, titled Biome-Al-dicine, the Present and Future with Generative AI for Biomedicine, represents the exciting intersection of biology, big data, and artificial intelligence, an area that is reshaping the future of biomedical discovery. What makes this event even more special is that we've been interacting with Dr. Sucheendra over several events online, and this is the first time we are meeting physically with him. And I'm sure we'll take the collaborations further from here. And I look forward to his lecture and look forward to a fruitful discussion. Thank you.
Now, I would like to introduce our esteemed speaker, Dr. Sucheendra Kumar. Sir currently leads the data science and engineering teams at SBX Corporation, Tokyo, as its Director of Data Science and Engineering. He is also an adjunct senior scientist at the Systems Biology Institute, Tokyo, Japan. He got his PhD in Computer Science from the School of Computing, National University of Singapore, and spent many years as a postdoctoral researcher in research labs across Japan and France. His current interests are broadly to understand complex systems and more recently in natural language processing, machine learning, and their applications in transforming healthcare and biomedicine. I request, sir, to please deliver your lecture.
Good morning, everyone. First, I'd like to really take the opportunity for the faculty, Dr. Yasha, Dr. Bhargava, as well as the Vice Chancellor, for actually organizing this lecture series. I'm very frankly, very surprised and humbled by the amount of preparation that has gone into this whole series. So I'd like to congratulate the whole team. I think you need to keep the spirit high with respect to this, and hopefully, as Dr. Yasha was saying, we could use this opportunity to start new collaborations and maybe interact with more students at the university. So a little bit of my background. So I've had a little bit of an interesting journey before I go in. I actually graduated in biotechnology many years ago. Okay, 2005 I graduated, but then I decided to actually pursue computer science after that. So, because of course bioinformatics was my calling, but then I realized that for a lot of things we need to do as bioinformaticians, you need to understand foundations of computer science, right? So this is why I actually went back to school and did my PhD in completely theoretical computer science, right? And then after my PhD is when I said, okay, let me then use all of that skills to come back and solve problems in healthcare. So this is roughly my journey. Of course, it's been over 12 years. I myself finished my PhD, so it's been a while. So this is what is my background. So why that was important is, so I largely come from a computational side of things, right? And I'm here to argue why I think now this whole phase of AI is something that each one of us needs to watch out for and also skill up. No matter what your discipline is, I think the new wave of AI is something that you need to upskill, right? And the whole idea of today's lecture is one, to give you a broad feel for this discipline. For those of you who already know it, it may be a little repetitive. And after that, I will be discussing some of our own work over the last 10 years that my group has been doing in Japan on trying to look at some of these aspects for solving problems in biomedicine. All right, so that's basically what it is. So before I go forward, how many of you are not using ChatGPT? Okay, great. Yeah, not using. That's great. I mean, because I think every one of us should, and the whole idea is every discipline needs to start using something like a ChatGPT, right? And so this is great setting for me because I don't need to convince you why AI is important. All of you are using it, right? So so the whole idea today is so I call it the Biome-Al-dicine. I just changed the E to AI because every discipline is going to have an AI in it, right? And so my goal is to kind of talk to you about, just rather than just use ChatGPT as your friend, what else can you do with technologies like ChatGPT, right? That's basically what I want to talk to you about. I think people have said enough, but I actually represent the Systems Biology Institute. For those of you who are not aware, we actually started the whole field of computational systems biology. Our boss, Dr. Kitano, actually started the field of computational systems biology. Those of you who have used Cell Designer, SBML for kinetic modeling, we all started that 25 years ago, right? In terms of the team, we are currently in 3 places in the world: Japan, Canada, and India. Japan is where a lot of the research team sits. India, we have a small but growing team of data scientists and engineers who sit here. And in Canada, we are based in the University of British Columbia, where we also have our research team sitting there, right? In terms of the kind of mix of people we have, people like me who are computer scientists, we have people who are biologists, people from biotechnology, so designers. So we have a very eclectic mix of people, and we believe that I think going forward, being tied to a discipline is also not a good thing. I think each one of us should become a problem solver rather than get married to a specific discipline, right? And that's a skill that is going to be more and more important. Even for you as biotechnologist, you need to be able to embrace other things that come your way, technology. You often get inspiration in other disciplines, right? And that's sort of the key. So while there is a lot of discussion on AI now, we should not forget that as biotechnologists, we already know that we are living in the century of biology, right? The level of detail at which we understand ourselves, our cells, all the way to how we are formed as organisms, all the way to how we interact as populations, starts with knowing biology about who we are. And most of us will probably live to 100, and most of that is because there's so much progress happening in understanding biology that translates to medicines and cures for diseases, right? And of course, I don't need to repeat this to you. Why is it so hard? Biology is complex, right? All the way from DNA all the way to the environment. And it is a partially observable system. By that, what I mean is, unlike a game where you know there are X number of moves, we don't know biology, right? That is what we do science. We understand what proteins do, what are their functions. It takes years and years of research. And recently, with a lot of data that is getting generated due to high throughput technology, genomics, proteomics, metabolomics, single cell level measurements, we are actually generating a lot of data, right? Previously, biology and biotechnology used to go at a certain pace. Today, because you're able to generate a lot of data about the underlying biology, you can actually turbocharge and actually make discoveries at a much greater pace, right? And the coming together of AI. And if you really think about what is AI at its fundamental notion, it is basically taking a lot of data, trying to make sense out of that data, and coming up with new technologies, right? So often the discussion in our community is, I think AI is great for biology, right? Because AI is a game of massive data, and biology produces massive data. So I think the next big wave is how are we going to take a lot of these AI techniques and apply it to biology, where a lot of you will be a part of that future. So as I said, we are able to now collect data at unprecedented level of detail, right? You can collect data at a phenotypic disease level, molecular level, genome level, chemical compound level, all the interaction across those layers. You can collect data in numbers, you can collect data, qualitative data, you can collect pictures, you can collect it as text, which is a lot of data that is in publications. Now, I don't know how many of you know that we are, the thing is, last week there was ChatGPT 5 that released. The theme is that from now, models are not going to get better. You know why? 90% of published literature has already been used to train models. There's almost no more written or printed text available on this planet to train models anymore, right? But that's not true for us. We have potential to generate massive amounts of data. And I am a strong believer that this is where the next wave of a lot of AI is going to happen. And you don't have to look further. Today, if you look at a Google, OpenAI, Microsoft, everyone focuses on problems for biology. They are looking at drug discovery. So those of you who have studied AlphaFold, right? This was by DeepMind, which is a Google company, right? They solved the long-standing protein folding problem that I think the whole community was trying to solve for over 5 decades, right? So I think this is going to change, and with tools that AI presents, I think we are going to see massive new changes that are going to happen in the way we do research in biology, right? And as I said, I think I'm just going to repeat myself here, but I think unlike before where AI was a buzzword, I think we are now living in a phase where it's almost similar to the Industrial Revolution. People often say that when people used to handcraft things, and there was the whole Industrial Revolution that came, which made it possible for things to be produced in mass scale, a very similar moment in history is with generative AI. So this is an old slide that I'm trying to use here, but 2 years ago when, I mean, and for all you know, all of this wave is just 3 years old. 3 years ago, when even we were using a lot of transformers for our own research, and the speed at which ChatGPT came and today we've evolved is just mind-blowing. Even for me who follows the field quite a bit, every week is new. Every week, the thing that I know last week is too old, right? And as students and future graduates who are interested in the computational side of things, not only computational, I don't think you need to be a bioinformatician to do AI. I think even if you're an experimentalist or a person who's trying to do reactor design, chemical engineering, biochemical engineering, you will need to embrace a lot of this, right? And of course, at SBI, so this is my boss, this is Hiroaki Kitano. We've actually proposed what is called the Nobel Turing Challenge. So the Nobel Turing Challenge was actually proposed by Kitano before this whole ChatGPT AI. 2016, he said, can we train intelligent models or algorithms which can do groundbreaking discoveries by itself? It's like machines trying to read a paper, understanding what the paper is, designing an experiment, doing that experiment in a robotics lab, then analyzing that data, then saying that, hey, the hypothesis that I had was right or wrong. If it was in the right direction, then refine, do more experiments, and then do that loop until it makes a discovery that is so grand that the Nobel committee would come and give it a Nobel Prize, right? So this is the grand challenge that Professor Kitano has proposed. You guys should read it to take inspiration in how future is going to come about. But this was actually proposed in 2016 by him, and he said it will take 30 years. In his paper, he said it will take 30 years before we get to that kind of a system. And for those of you who are following, last year's Nobel Prize, 2024, for chemistry as well as physics was in some sense a proxy for this, right? The Nobel for physics was for the whole class of neural networks, which was the basis on which the new AI models are run. And the chemistry Nobel Prize, interestingly, was for the protein folding problem, right? So I think we are there where humans who used AI have already won the Nobel. So it's about now machines trying to become more and more intelligent, where they can do science and do groundbreaking discoveries. So I think that is what is really, really interesting in the times we live in. So so then the question is, I have said enough. What would a future where the AI is mainstream would look like for all of you guys? When you go into research, when you go into pharma companies, when you go into bioprocess companies, what is it that this technology can do for us. And below, actually, I've mapped the whole life cycle of the value chain of the whole flow of how, let's say, a drug discovery, for instance, where it starts with research or drug discovery, then there's preclinical study, then drugs are taken through into clinical trials, they go through filing or approvals, which then goes into launch or sales, and then goes into point of care or hospitals, right? Now, in each of this, I think AI has a role to play. And my goal today is to very quickly take you through what that means, right? And I often, I'm a big fan of the Matrix movie. So how many of you know when Morpheus and Neo have a discussion and he asks, do you want the red pill or the blue pill, right? He says, it's very similar to us, right? So the way I look at it is, one of them tells you all the pros of why AI in biomedicine is great. The other is telling you that, hold on, I think we need to take it cautiously, right? So I'm going to make a case for both. So first is the positive case. So let's take, as Neos of the future, let's take the red pill and see how far or what are the things that you can do. Right, some terminology that I want to set straight, because often it's a little abused word, right? This whole spectrum. So AI is essentially around for many, many, many decades, right? It's a very broad term which tries to look at how do you incorporate human intelligence into machines. So in the 1960s, we used to have the dendral and metadendral system, which was just encoding rules. That was also AI. And then there is a small field inside, which is machine learning, where you're trying to essentially use data and then train algorithms which can model that data and then generalize it enough so that it can start predicting, right? There's nothing more to it, right? What do you do in machine learning is the journey of what you study after that. But essentially, taking data, modeling it, trying to find patterns in it, using that patterns to predict. That's machine learning. Deep learning is again a class of algorithms that is specifically something, interestingly, it actually came up 2.5 decades ago, which is what Jeff Hinton and his team got the Nobel for. But thanks to the compute power that we have today, it has come to the center stage. And it is a very, again, a sub-domain there which looks at neural networks or trying to work with neural networks as the main base. And the new Gen AI, which is all your chat GPTs of the world, is to formulate the deep learning mechanism of things into a specific formulation where you use it as a generative task, which is when you give a seed word, it just then generates based on some distribution, right? So this is a terminology that I find people often don't fully appreciate. So I think it's important for you as students to remember. And as I was saying, why is all of this possible now? Why is this whole AI becoming such a big thing, right? It's actually, I would say, the single biggest reason is NVIDIA, because they gave us a GPU power that's actually changing the game quite a bit. So here, what you see, I mean, you don't need to get into the details, but this is years mapped here, and the training compute time. So think of it like how powerful are your NVIDIA GPUs. I shouldn't use NVIDIA as a brand, but and you will see that 2010 is when the whole deep learning era picked up. And then 2017, there was a very important paper from Google, which actually talked about neural networks, but the paper was called Attention is All You Need. That actually set off this whole field. And that was around the 2017 time. So all of this is because the new fuel here is GPUs, right? And people with the best GPUs are really pushing the game. As a practitioner of this field, I find that really no fundamental change has happened in terms of the technology of neural networks that have been used. It's just about small tweaks here and there that are taking us steps ahead. Again, this is an old slide, but the point that I'm trying to emphasize is the field is moving really, really fast. While every time an OpenAI comes with a closed model, there is a big competition that's happening on the open source world where researchers are trying to take that and giving it away to the community. And I think this has set up a very healthy kind of innovation cycle. And most of us here who are a little computationally inclined, I think for us, even in your gaming GPUs, you could now train, fine tune, and run some of these models, which are very vertical for, let's say, a biotech use case, right? So that's where we are in terms of the maturity cycle. Now, I'll probably share these slides later as well, but I think for every sort of process that I had mapped before, where it goes from research all the way to point of care or healthcare ecosystem, AI has a definitive role to play, right? This includes even doing experiments. Today, we are actually working on a project in Japan where we are actually for the gut biome, we are actually building an end-to-end robotics lab, which means from when you take a stool sample to when you prepare it for DNA sequencing all the way to analysis, we can now have robots do that whole process, right? So things are really moving fast. So next few slides, I want to give some examples, especially for those of you who think a ChatGPT or these generative AI models are only about text or asking it some question for which you have a companion. I want to give some early applications of where very similar things, right? So think of what is English? It's few letters put together and that's the language, right? And we write everything. Similarly, we have this similar alphabet for life, right? Your DNA is 4 letters and then that whole organization. I mean, I call it the exactly same thing that we humans do. Evolution has done it, the biology has done it at scale. So this particular work is not by our team, but this is just a representative where they actually looked at how COVID variants mutate. So if you look at how you had these variants, the alpha, the deltas, the COVID variants, they were essentially mutations that were happening in these base pairs, right? That led to these mutants. Now, if you really think about it, if you're able to take millions of these, millions or hundreds of millions of these sequences of viruses, and then you track its evolution of mutations over time, you should also be able to predict, given today, how is that mutation going to happen, right? So this was some really good work that happened in, I think, 2022, if I'm not wrong. 22, where they were actually able to build genome scale language models. So ChatGPT is called what is called the LLMs. This is what is the Gen SLMs, right? Genome scale language models, where the language is defined by the number of letters of the base pairs, right? So the other one is, I think what we already spoke is the whole aspect of what won the Nobel Prize, right, for protein folding, the AlphaFold 2. But interestingly, of course, AlphaFold looked at the protein folding problem. There is also the whole part of drug designing, which is you dock compounds with proteins in their different configurations. And then this is also a very, very cumbersome and laborious process. And there are some new architectures that have come where the whole task of molecular docking is actually posed as a Gen AI task. And there's some great work happening here. It's not only research. A lot of startups have come out from taking this into the pipeline where they're coming up with a lot of lead molecules that can be taken to clinical trials faster. So similarly, another interesting application that I found is on the whole aspect of conducting clinical trials. So typically when a clinical trial is conducted, a big component of a clinical trial is to do cohort selection, which means you want to select who are the responders, non-responders. Oh, you need to create those groups, right? And many times it's not a very well thought through process. This particular piece of work, although is not Gen AI, but what they were able to do was to start looking at very large data sets of clinical trials and use that to come up with on the fly trial eligibility rules so that you could increase the number of patients who could be a part of that trial, right, which would have missed otherwise, right? So what is the advantages of this? This one, in fact, again, has already seen the light of the day. This research was again 3-4 years ago. Today, a lot of clinical trials go through this pipeline, at least for some of the big pharma I know, who actually use some of these techniques for patient recruitment, right? Similarly, a big application of Gen AI in healthcare and biomedicine is in synthetic data generation, which means just like it generates your essays or it is generating your other things that you want to look at, you can think of using Gen AI models for a synthetic data generation because, as I said, models are only as good as the data that you use them. And sometimes if you're able to understand the underlying data well enough, where I'm not able to explain, but I'm able to model it, then that can be used for data generation, which can in turn then be used to train better models, which can get that whole loop going, right? So this is another area where there is a lot of work. I think this is another very classic use case. A lot of applications in medical imaging and diagnostics of Gen AI, both in terms of being able to use it for synthetic data generation, but more importantly, trying to really accelerate this whole field, right? Now, another very big application, and I think this is an obvious application of Gen AI, is in looking at text, right? Now, text, where the text is from scientific literature, is something that my group is very interested in. And we are trying to look at how you could use a lot of the new tools and techniques at disposal, but to look at what is published, the publications, right? So most of us know that you can't just keep up with the rate at which publications are happening, even if you are working in a very small field, right? How do you then use some of these tools to help scientists and do research is something that I personally am quite interested in. And a lot of my research over the last 7-8 years has been on this aspect, even before the whole Gen AI thing took off, right? So this part, I stop a little bit of the generalization of the field and come to a little bit of what we do at the Systems Biology Institute. So as I said, one of the things that we focus on is on this whole aspect of Nobel Turing Challenge, where Professor Kitano actually posed it as what does it take to build intelligent machines which can eventually do discoveries which are worthy of a Nobel Prize. And the Turing Challenge is that, so those of you who know the Turing Challenge, it is a discovery where you should not be able to tell whether it was done by a human or a machine. So that's the Turing aspect to that Nobel Turing Challenge. And so this is one sort of slide in his 2016 paper where he talks about what would such a system look like. And a lot of biologists would relate to it. Is typically any lab would have some sort of a hypothesis by reading papers that the PI usually has. A lot of that paper knowledge is in the PI's knowledge base, if you will. So a lot of that knowledge is embodied either using tools or the PI has an understanding of that knowledge. Using that, using what is already published, usually they come up with a hypothesis. They say, hey, it's because of this and this and this. Maybe there is this mechanism in terms of how these proteins are interacting, for instance. Then they would go ask their grad students and their lab to do experiments. Then they would do a data analysis of these experiments. Then they would say, hey, the hypothesis worked. They would publish a paper. If it didn't work, then they would go back to refine that hypothesis. And essentially what you do is, as you go through this cycle, you end up, it's almost like a hypothesis generating machine. You generate the hypothesis, you validate, you use that data back, you write papers, and then as you turn this wheel, science gets happened, right? And so when my group looks at things, we look at which parts of this life cycle can we use intelligent algorithms to work on. And today, I think I'm going to focus on 4. I've just highlighted 3. But I'll show you the work that my lab has done on some of these aspects where you see the stars. I'm going to run very fast from now. I know I'm also short of time. So the first aspect that I'm going to talk to you today about is how we've used LLMs or these Gen AI models for knowledge extraction. So you input a paper, you get an output as a graph. The graph is everything about that paper understood as a network, right? So that is one. The second is where from a paper, can you extract laboratory protocols automatically, but not just extract, but make it in a way that it can go and run in the omics systems that you have, right? So that is another piece of work that we published. This was when it was an archive, but it's already published. We're also looking at how do you work on hypothesis generation. So once you have taken all the knowledge that is in the papers, a hypothesis generation would be, what is the new potential discoveries? So that is another thing that our team is working on. And the last one is, I personally am very passionate about this, which is, especially in bioinformatics, reproducibility is a big problem. I mean, even I know that almost 60-70% of papers published have a lot of asterisks or conditions apply, where it would work only in a very specific setting, right? And it's almost impossible to actually follow through. Nobody, a new graduate student who comes and tries to build a new algorithm, they would take it for its face value and try to build on top of it. Now, how do you bring a little more of sanctity there is something, again, that we have been working on, which is, if you take a paper as an input, can you actually generate, just like ChatGPT generates text, can you generate all the code, the bioinformatics pipeline of that paper and reproduce the results that was there in that paper, right? So for this aspect, we focus only on data analysis papers or bioinformatics papers, but that's the idea, right? So this is work that we published 2023. In fact, interestingly, 2023 is when ChatGPT came. And luckily, we got this paper accepted before ChatGPT came out, because we had no choice. If ChatGPT had come out, this paper would have got rejected, because what we had done was model the problem very similarly, like how ChatGPT had done, where the goal was to actually, in the pharma space, toxicology prediction is a very important task. What a lot of toxicologists in pharma do is actually read a lot of papers and establish, hey, this compound is toxic in this setup with this experimental condition. All of this is extracted and then used in conjunction with other computational techniques. So this is a pain point for pharma, right? You have departments where they would have hired a few tens of toxicologists whose job is to only update their internal knowledge base by extracting, reading papers and putting that in. So what we actually trained was a BERT model. This is sort of the genesis of the new class of generative models. We had actually trained a BERT model specifically for this task, where the input is a publication and the goal was to establish if there was a chemical that was mentioned and whether that chemical was deemed mutagenic or not, and the experimental conditions associated with it. And this work actually is done with a pharma, very big pharma in Japan. And this is a system that's already, again, I mean, the speed at which 2023, today we have the system running and powering their toxicity mutagenicity analysis, right? So what we did was, the summary that you need to take away is using a lot of Gen AI models, we are able to take the accuracy really high. Not only that, there is often a little bit of a complaint that these models are like black boxes. There's an input, there's an output. It doesn't tell you why a model told you why it made a prediction. So we actually came up with an explainability layer here. So what you see here is the text that the model used, and the red indicates that particular model was mutagenic, blue indicates it was not mutagenic, and then the distribution of the color actually tells you which were the words that were used by the model to decide whether a particular chemical it understood was mutagenic. And there's a whole set of work that's happening on explainability, and this is something that we had done 7-8 years ago. Similarly, this is another very similar kind of an idea, but here the goal was to look at the gut biome and trying to look at the gut disease sort of interactions, again, completely from text. Right? So you would basically have thousands of papers going into the system. Output would be a database, right? Very simply, right? Which is a lot more accurate. Again, this is work that's published, and we were able to show that we were at the best at that time. I'm sure there are systems better than us today, but when we published this, we were sort of the state of the art. And another aspect of what we do a lot in Systems Biology Institute, and you must have known the KEGG, the reactome, all these pathways, most of you may have read. All of these pathways were actually people putting together, reading a paper, putting these interactions together, right? So we actually, and SBI has traditionally been sort of the founder of this whole field, as I said, of building very large scale maps 20-25 years ago. So we actually said then, can we use these models now to build these maps, right, automatically, right? And this is also work that's already published, and we are now able to do a really good job on trying to build these pathways directly from text. So I'll skip this very similar work that we did. And if I'm not wrong, I think Dr. Yasha actually edited this, was an editor of this publication. So the first part was on knowledge extraction, which is you extract the knowledge that is in papers, but at scale. You're looking at millions of articles that can go into some of these systems, right? That's the scale at which we operate. This work is, hey, it's great. I have knowledge about things that are already known. Now, how do I use it to come up with a new hypothesis? A new hypothesis is a potentially new discovery, right? If it is tested and validated. And this is actually with my friend and a big team that's actually now in Sony AI. So it's joint work between my team and Sony AI, where what we do is we encode this knowledge with a lot of the previous work that I showed you as a very large knowledge graph. So this is all of science for a specific field, right? Then we say that a hypothesis essentially is about looking at finding new links. It's like in Facebook, you often get that this person may be your friend. It's very similar, right? What we are trying to do is we are trying to model all of the biological concepts and then trying to say that, hey, something that was not known before maybe is a new discovery. So that's the problem formulation. I think I'll probably skip this. It's a lot technical, but what we do is we model it as a temporal graphlet. So you think of it like today I had some knowledge, 5 years later I have some knowledge, 10 years later I have some knowledge, right? By knowledge I mean new publications are coming, the graph becomes bigger and bigger and bigger. So can I learn the way knowledge is growing in a yearly interval and then use that to predict the future, right? So that was the problem statement. Yeah, we were able to come up with a new algorithm. I'm going to skip it. But the main point to note here was, of course, I mean, even Facebook uses very similar algorithms to tell you who your friend may be, right? So we actually benchmarked with a lot of these algorithms, and we were sort of the best algorithm out there. This is again work that's probably 5-6 years ago, right? A lot of based on our work, the whole field has opened up. A lot of other publications have come in. But we were able to show that you can actually model this in the formulation that we postulated. And now we are able to, it's not great yet. Of course, there's still a lot of noise. But I think the next 5 years, I think we are really going to be at a space where the hypotheses that are generated by some of these models can be taken with a reasonable amount of confidence to do experiments. In fact, as we speak, some of the experiments hypotheses we've generated on aging are being tested today. But this one, I just want to show you one thing. So think of two concepts. Let's say Raynaud's disease and fish oil. Okay, completely unrelated topics. But we actually broke up the publications of 1970 to 79, 80 to 89, 90 to 99. And as I said, the goal is to predict 99 to 2005, right? What would be, or how would this knowledge be there? And what you saw here is the actual discovery of this relationship was in 1985. This is when a paper that talked about this relationship came out. Now, if you look at our algorithm, the first row tells you what is the probability that the algorithm gave for this hypothesis to be true if I consider 1970 to 79. It was a very low. And as you gain more knowledge, you see that the confidence level increases, which means the algorithm is able to learn and embody a lot of that knowledge and use it for prediction. All right. So this was basically what was the main thing. The third aspect, so one is knowledge extraction, second is generating new hypothesis. Once you generate new hypothesis, what do you need to do? You need to go do experiments, right? You need to then go do a 3-year experiment in your lab, right? So here again, we found out that if doing bioinformatics is underspecified in papers, actually doing experimental all the experimental parameters going into paper is another big problem, right? Sometimes it's just honest mistakes that percolate. It will then take many years of a grad student or a postdoc spending time on trying to replicate a previous experiment. So the goal here was, can I now take a publication which reported experimental procedures and then extract information from it so that it can generate the protocol automatically, not just generate in terms of extraction, but also the gaps that were there in the protocol, which hindered it from a grad student doing a few more experiments. Can we actually learn from a whole stack of other papers on what those parameters should be? And I'll cut it short. We again trained a model. This model actually was published in an automation first journal. And last year, it actually won the Editor's Choice Award because of the way we had formulated this problem, right? The last part of what I wanted to say from our own work is on the part I told you on reproducing science, right? Which is, let's say you had this paper which talked about analyzing a lot of RNA-seq data, and it had a hypothesis that it formulated, right? Now, how do you give this as an input to an AI system, and can it come back and say, hey, these are the problems, I could not replicate it, or I could replicate it. What the author said is what I was able to judge. And This is where the whole field now, I think most of you must have heard of agentic systems, right? Post ChatGPT, now the new buzzword is agentic systems. And we were actually able to formulate this problem of reproducibility as an agentic AI sort of problem, where we sort of broke down what does it mean to read a paper and replicate or do bioinformatics analysis. And then we created agents. One is a reader agent, one is a technical data technician agent, one is a programming technician. So we gave roles, and then we let them have roles about what they are good at, and then they would all interact with the goal of either saying the paper is bad or we were able to replicate that paper, right? So this is what we did. I will again skip this because, of course, this is 2 years back. There were still problems with the stack. Today it's getting much better. My team is now building this whole thing full scale. We should be publishing something soon in this, very, very soon. The last part, of course, a lot of research and things that have been told. The last part is on, okay, as students, as faculty, as postdocs, as PhD students, what are some of the tools that you guys can start using as a part of your own learning and knowledge gaining, right? This is just a few tools that I thought was interesting, and especially those of you who are inclined on bioinformatics should start looking at it. I'll skip this. This was for another audience, but so for instance, there is some good work on doing academic literature survey. Of course, even ChatGPT can do, but if you really go into details, you will find how much mistakes it makes, right? So there is a lot of interesting work happening on trying to break this problem very structurally, and then using that to do academic survey, do literature search. And I've listed some of the tools here. Please, those of you who get access to this deck, have a look at them, use them. We use it quite a bit. A lot of commercial services for those of you who don't want to open up, do the things. A lot of very good services like Elicit, Consensus, where you can analyze your ideas, analyze research papers very well. And these have what I crossed what I call the chasm of being useful. All of them are quite useful and help accelerate, and even for learning, they're really, really good. Again, interestingly, for bioinformatics, specifically for bioinformaticians, there's a really good amount of work that's happening on basically converting bioinformatics pipelines and tasks into a chat interface. You should say, I have this data. I want to know, come up with a mechanistic thing that I want to know if this protein inhibits this. Then it would come up with its own way of saying what all it should analyze, what is the statistics I need to apply. All of this, there's some very, very good work happening that I hope you will also follow. Like this is a very nice one, bioagents, where the whole end-to-end bioinformatics analysis can now be converted into a multi-agent kind of a setup. And this one is very user-friendly, so you can use it off the browser. So for those of you who don't want to spend time setting up things, you can look at it. And this is something that I want to sort of use this as my last few slides. So this is actually DeepMind's work, 2025, Feb 19, 2025, where, as I said, this is a field that is of a lot of interest for a lot of deep tech companies, where what they want to do is develop a co-scientist, right? And very similar to our own research on reproducibility, they have now come up with a multi-agent AI system, which at least for now they say is a co-scientist. It works with the scientists to make them a better scientist. And using this, interestingly, this is where it gets very, very interesting, where it's no longer just about the algorithms anymore. They were able to use it for drug repositioning, new target discovery, and these have already gone on to come up with lead molecules or drug repurposing, where it actually showed some really, really good results, right? So it's no longer about just research that's not seeing the uh, light of the day. It's already really advancing at a rapid pace. Now, great. I told you why it's all great, why we should all be so excited about AI. Now I'm here to tell you why we should take it with a pinch of salt, right? Which is the case where we say we take the blue pill and we go back to sleep and nothing happened, right? Now, so some things that I've already covered, right? Gen AI models are still a little bit of a black box, all right? Every time you change a prompt, your reply changes for a chat GPT, right? The whole field of prompt engineering tells you how you should talk to that model. And those of you who are on social media, last week there is a big fight between Sam Altman and Elon Musk, right? Because Elon Musk has his own AI model called Grok, Sam Altman GPT-5, and there was a fight between Sam Altman asking whether he's trusted or Elon Musk is trusted, for which GPT-5 said Elon Musk is trusted. And when Elon Musk was asked on his AI model who is trusted, it said Sam Altman is trusted. So, so this is actually summarizes the problem also with AI, right? So we need to always take it with a pinch of salt. So there are issues of data privacy and security. Just with any machine learning model, these models are as good as the data on which they were trained on. For instance, a lot of these models may not work very well in Indic languages. That's because the first versions of models were largely on English as a language. So it has these biases. I don't know. In fact, I think last year when Prime Minister Modi was in Paris AI conclave, he actually talked about, can you generate an image of a left hand writing? I don't know, those of you who followed. All of the AI models which do image generation were you trained on right hand. If I told you generate a picture of somebody writing, it would always generate a right hand person writing. If I prompted it, generate an image of a person writing with left hand, it cannot generate. That's because data in is the data out, right? So this is especially relevant for biomedicine because that is the data trade-off. Lack of transparency, regulatory and legal issues come up. And this is, again, all over the place. Integration and implementation of these solutions are still not a solved problem. So those of you who know machine learning, there is this saying for long practitioners that all models are wrong, which means no matter what you do, they will all go through something called the model drift or data drift. So there's a lot of work to be done there. And of course, today, the person who is wealthy enough to buy the GPUs is the one who's winning the AI race. So we need to work on models which are more cost effective, compute effective, data effective. So there's a lot of work to be done there. And I don't know if you're again following, last week ChatGPT 5, the first version of ChatGPT 5 was way dumber than ChatGPT 4. Then they tuned it, right? So it has hallucinating quite a bit. So again, this is challenges that the whole community is trying to address, and it's going to become even more important as a lot of you go into the workforce with these powerful tools with you. You have to be very careful. And a few more examples of how with malintent things can go crazy. There was like, you could now design even toxic agents as simply as designing novel drugs, right? And this is one thing I really like. For those of, especially for healthcare, I don't care if my essay was a little bad or not, but when you're trying to make those decisions for healthcare, these things become extremely important, right? And this one article actually stood out. So I don't know how many of you have watched the movie Oppenheimer, which was around the whole atomic bomb and how this guy who actually did the first research around that technology then went on to feel remorse around what it means. I don't know what I did. AI is not good enough to fix this. Last few slides. I think, yeah, last slide. Okay, so thank you so much for your time. This is a cartoon I love. You should probably just read and enjoy. Yeah, thank you. Open to any questions you may have. Yeah. So I want to give it a two way to answer it. So of course, today you must have used the whole ChatGPT to generate images. It's doing a decently good job, right? But then what I think about it is whatever we were able to do so far, it may be able to do well. Of course, there is the whole concept of AGI, which means can really machines be as intelligent as us? I don't think we are close to that. It would take many years, at least 5 to 10 years, right? Where we at least start thinking about these things, about whether it is as intelligent as humans. But I think it is the way I look at it, I also think about it a lot. The way I think about it is, it actually questions what it means to be a human for us. What we thought was white collar jobs was probably as easy as training a model now. So we have to evolve what it means to be intelligent. It's not about being able to read and write. It's not about, so I think we need to start thinking about what it means to really be human. Machines will really get very close. Even emotion, I don't know if you follow, 1.5 years ago, you could, a lot of voice synthesis, you could know that there is a robot talking on the other side. Today I can tell you, you just cannot tell who's the other side. In fact, a lot of this is being used for therapy, for a lot of mental health. And so what I mean by that is when I talk, there is an emotion in my voice, right? Which was very hard for machines. Now they've gotten so good. So I think, yeah, we are getting close, but then it also challenges us about what it means to be really intelligent. So it's a hard question, and that's all I can tell you. So biological systems is a billion years of evolution. AI is just a few 50, 60 years. So we are way more better to handle, we are more robust. So everything that I told you in the last 3-4 slides are why there are going to be challenges. It's like great, it's going to drive a lot of business, but I mean, biology is doing that at evolution scale. So it's very similar, right? I mean, but AI is still black box. Biology, there are mechanisms, the underlying physics, chemistry is involved. We are trying to understand what it is. So, yeah, so that's what I think. Okay, great, thank you.